Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
Right now, Voyager 1 is racing through complete darkness at 38,000 miles per hour, farther from Earth than anything humanity has ever built. Its power is fading, and by late 2026, its signal will need an entire day just to reach us. But before Voyager 1 falls silent forever, NASA confirmed it detected something hidden in deep space that could change everything we thought we knew. The signal that almost disappeared forever. On the 18th of November, 2026, at 2:16 in the morning Pacific Standard Time, Voyager 1 will cross a distance of 16,094,799,096 miles from Earth. That number has a meaning that hits differently when you translate it. It is exactly one light day. A beam of light, the fastest thing in the known universe, will take 24 hours to travel from Earth to the spacecraft. Any command sent from Mission Control at that moment will not arrive until the next day. Any reply will not return until the day after that. A single conversation will take 2 days, and that spacecraft will still be out there, still measuring, still transmitting with the power output of a dim household light bulb, still carrying the golden record bolted to its side with its greetings in 55 languages, the sound of rain and surf, the cry of a newborn child, 90 minutes of music spanning cultures and centuries, and a pulsar map engraved in a language of physics that points back to our sun. For now, most people have no idea how close we came to losing Voyager 1 completely, and the fact that we almost lost everything this spacecraft discovered in the deepest reaches of space because of a component that costs less than a cup of coffee should unsettle every single one of us. On the 14th of November, 2023, something went wrong. Voyager 1 was still transmitting, still sending its carrier signal back to Earth, but the actual data, the science, the measurements, everything meaningful, collapsed into gibberish. The stream turned into a repeating nonsense pattern. For 5 straight months, the most distant human-made object in existence was speaking, but no one on Earth could understand a single word. Engineers at the Jet Propulsion Laboratory in Pasadena started tearing through the problem. Every diagnostic command they sent took over 22 hours to reach the spacecraft. Every response took another 22 hours to come back. That meant every single question and answer cycle consumed 2 full days. There was no quick fix. There was no rebooting the system from a desk. This was brain surgery performed on a patient that was over 15 billion miles away, with a 2-day delay on every hand movement. They eventually traced the fault to one memory chip inside the flight data system. That single chip had failed, corrupting roughly 3% of the spacecraft's total memory.
And it seems to be a hardware problem, one of the chips on board and part of the flight data subsystem.
3% does not sound like much until you realize that Voyager 1's entire computer holds 69.63 kilobytes. Your phone's cheapest app uses more memory than the entire brain of humanity's most distant explorer. The team did not know whether the chip died from decades of cosmic ray bombardment or from simple old age after 46 years of continuous operation in the most hostile environment imaginable. What they did next still feels like science fiction. They obtained a complete memory dump from the spacecraft, mapped exactly which sections were damaged, broke the corrupted code into fragments small enough to fit into the remaining healthy memory locations scattered across the system, rewrote all the internal references so the computer could find its own instructions again, and transmitted the entire surgical patch across 15 billion miles of void. They even deleted old software routines from the 1979 Jupiter flyby to free up space. Programs that had not run in 44 years were erased to make room for survival. On the 20th of April, 2024, readable data came back. 5 months of silence, broken by a stream of clean engineering telemetry. Science data followed in the weeks after. Suzanne Dodd, the Voyager project manager, called it one of the most serious problems the mission had ever faced. She was not exaggerating. Think about what was at stake. If that repair had failed, every discovery that Voyager 1 had made in interstellar space and every discovery it still had left to make would have ended right there in that moment. 46 years of survival against impossible odds, erased by a chip that probably cost pennies when it was manufactured in the mid-1970s. The spacecraft survived, but the power keeping it alive was already slipping away, and the next sacrifice was not going to be a software routine from the 70s. The instruments that had to die. You need to understand something about Voyager 1 that makes every remaining measurement it sends back almost painfully precious. This spacecraft runs on 3 chunks of plutonium-238. When it launched in 1977, those radioisotope thermoelectric generators produced around 470 watts. That is roughly enough to power 4 old incandescent light bulbs. The entire exploration of interstellar space has been powered by the energy equivalent of a few light bulbs in a hallway.
Plutonium-238, an isotope unlike its bomb-making counterpart. This isotope could be harnessed as a safe lifeline for spacecraft venturing into the darkest, coldest corners of the solar system.
By 2026, those generators produce somewhere between 200 and 220 watts. They lose about 4 watts every year. That decline is not a malfunction. It is physics. Plutonium decays. The thermocouples that convert heat into electricity degrade. There is no solar panel to supplement them because the Sun, from where Voyager 1 sits now, is just another star in the sky. On the 17th of April, 2026, NASA commanded the Low Energy Charged Particles instrument to shut down. Not because it was broken, it was working perfectly. They turned it off because there simply was not enough electricity to keep it running alongside everything else the spacecraft needed to stay alive and oriented in space. That instrument had been collecting data since before most of the people reading this were born, and it was sacrificed to buy a few more years for the magnetometer and the plasma wave subsystem. The last 2 science instruments still operating. Of the original 10 instrument packages Voyager 1 carried when it left Earth, 7 had already been turned off one by one over the years according to a priority list the team had agreed on long ago. Every shutdown was a small death, a permanent loss of one way of sensing the universe, and every shutdown bought time for the survivors. The engineering team was also working on something they internally called the Big Bang, a risky procedure that would simultaneously reconfigure multiple powered systems on the spacecraft, swapping some components for lower power alternatives while keeping enough heat flowing to prevent the propellant lines from freezing. They planned to test it on Voyager 2 first because Voyager 2 carried a slightly better power margin and a shorter communication delay. If it worked, they might attempt the same procedure on Voyager 1 no earlier than July of 2026. Success could even bring the Low Energy Charged Particles instrument back to life. Failure could mean losing attitude control or thermal stability permanently. Kareem Badaruddin, the Voyager mission manager, put it bluntly: shutting down a working science instrument was never the preferred option, but it was the best available way to keep data flowing from a place no other spacecraft has ever reached. The mathematics of power decay does not negotiate. By the early 2030s, even one science instrument will no longer be sustainable. And that means the window for understanding what Voyager 1 is actually detecting out there is closing fast. So what exactly has Voyager 1 found that makes this slow death so agonizing for the scientists who depend on it? The answer starts with a sound that should not exist. The hum no one expected to find. When Voyager 1 crossed the heliopause on the 25th of August, 2012, it became the first human-made object to enter interstellar space while still transmitting data back to Earth. At roughly 122 astronomical units from the Sun, the particle instruments recorded a 1,000-fold drop in solar particles and a simultaneous surge in galactic cosmic rays. The plasma wave subsystem later confirmed a 40-fold jump in electron density. Linda Spilker, the Voyager project scientist, described the crossing as the spacecraft stepping outside the only home our species has ever known. After that historic moment, the plasma wave subsystem picked up occasional plasma oscillations. These were brief, intense bursts, like electrical whistles triggered whenever a shock wave from the Sun raced outward and slammed into the interstellar medium. They gave scientists quick snapshots of the plasma density outside the solar system, but they were sporadic and unpredictable. Then something changed. Starting around 2017, a different signal appeared in the data. It was faint, narrowband, sitting near 2.5 to 3 kilohertz, and it did not behave like the shockwave whistles. It did not flare up and disappear. It just kept going, month after month, year after year. Across more than 900 million miles of travel, this thin, continuous emission persisted just above the noise floor. Stella Koch-Ocker, a doctoral student at Cornell at the time, was the one who spotted it. She was going through archived plots of the plasma wave subsystem data when she noticed a faint line that did not belong. She later said she thought she was starting to see things. She was not. She had just discovered something no human being had ever detected before: a persistent plasma wave humming through the void of interstellar space. The paper she and her colleagues published in Nature Astronomy in May of 2021 confirmed the detection and revealed what it meant. That continuous hum allowed the first ever sustained measurement of electron density along Voyager 1's path through interstellar space. And the density was not smooth. It showed fluctuations on scales of astronomical units and a large-scale gradient that told a story nobody had anticipated. Near the heliopause, the electron density was higher than models had predicted, consistent with a compression effect, a snowplow pileup of interstellar material being pushed and squeezed by the advancing edge of the heliosphere as our sun plows through the galaxy. James Cordes, the senior author on the paper, described the interstellar medium as being like a quiet, gentle rain. The solar shock waves were the lightning. Between the storms, the rain was always there, steady and previously invisible to every instrument humanity had ever built. Think about that for a second. For decades, textbooks described the space between stars as essentially empty, quiet, dead, and a 40-year-old spacecraft carrying less computing power than a modern digital wristwatch proved that the void is alive, humming with a continuous signal that we never had the technology or the position to detect until now. The hum was extraordinary, but what the magnetometer was recording at the same time was even stranger. The magnetic mystery that broke the models. Every serious model of the heliosphere built before Voyager 1's crossing predicted the same basic thing. The magnetic field inside the solar system, generated and shaped by the sun, and the magnetic field in interstellar space, shaped by the galaxy itself, were two separate systems. When Voyager 1 crossed the heliopause, the boundary between those systems, the magnetometer should have recorded a clear rotation in the direction of the magnetic field. The solar field points one way. The interstellar field points another. Crossing the border should have looked like turning a corner. Voyager 1's magnetometer registered almost no rotation at all. The field direction outside the heliopause was nearly identical to the field direction inside. And when Voyager 2 crossed on a completely different trajectory 6 years later, it recorded the same puzzling result. Subsequent research, published in the Astrophysical Journal and other publications, revealed a far more complicated picture than anyone had drawn on a whiteboard. The evidence pointed toward a thick boundary layer of reconnected magnetic flux, a region where the sun's magnetic field lines and the interstellar field lines had merged and reconfigured into nested islands and complex structures called separatrices. Voyager 1 may still be traveling through a zone of magnetic fields that were once connected to the sun, but have been rearranged and rewoven far from the original crossing point. The boundary between our solar system and interstellar space was not a wall. It was a tangled, dynamic interface where energy and magnetic architecture exchanged across the edge of our star's influence in ways that no model had anticipated. One study published in 2026 concluded that the Voyager measurements, as they are currently interpreted, remain almost impossible to reconcile with the global interstellar field orientation inferred from the IBEX energetic neutral atom ribbon, a completely separate set of observations made from near-Earth orbit. Two completely independent ways of measuring the same magnetic environment were producing answers that refused to agree with each other. That kind of contradiction does not get swept under the rug in astrophysics. It means either the measurements are incomplete or the models are fundamentally wrong, and both possibilities should make you pay attention. L.F. Berliga and colleagues tracked additional evolution in the data, including a magnetic pressure front jump that began in 2020, elevated field strength lasting years, and a gradual shift toward more statistically uniform behavior after 2022. Even at distances of 165 to 167 astronomical units, the interstellar medium still carried the fingerprints of solar activity. The Sun was reaching out beyond its own border, still shaping space it was never supposed to control. And the temperature readings from that same region made everything even harder to explain. The burning void that cannot burn. Both Voyager 1 and Voyager 2 recorded plasma temperatures of 30,000 to 50,000 Kelvin in the heliosheath and near the heliopause. Some popular accounts called it a wall of fire surrounding the solar system, and the phrase stuck because it sounds terrifying. 50,000 Kelvin is roughly 9 times the surface temperature of the Sun. But calling it a wall of fire is deeply misleading, and understanding why actually reveals something far more interesting about the nature of space itself. Temperature in physics is a measure of how fast particles are moving. In the Helios sheath, the particles are screaming fast, carrying enormous kinetic energy. But the particle density in that region is roughly 0.1 particles per cubic centimeter. To put that in perspective, every breath you take on Earth pulls in something like 25 quintillion molecules. In the Helios sheath, you could fly through a volume the size of a football stadium and encounter maybe a handful of particles. Collisions between particles are so rare that the spacecraft experienced zero meaningful thermal load. No heat transfer occurred. The high temperature was a speedometer reading, not a furnace. The same sparse superheated plasma carried the continuous hum and the unexpected magnetic field alignment. Solar-generated pressure fronts and shock waves continued to push into this medium years after both Voyagers had crossed the heliopause. One event in 2020, designated Pressure Front 2, triggered the multi-year magnetic hump that Berlaga's team tracked in the magnetometer data. Models driven by solar cycle data showed that large-scale compressions from the Sun striking the heliopause could reproduce the observed structures in the interstellar medium. The space immediately outside our solar system was neither empty nor quiet nor independent. It was a living, breathing boundary that still responded to the rhythms of our star, a place where the Sun's influence did not end cleanly, but rather faded in layers and echoes across billions of miles. Everything we thought we understood about where our solar system ends and where the rest of the galaxy begins turned out to be a rough sketch of something far more layered and far more alive than the textbooks ever suggested. Everything Voyager 1 has discovered over the past decade, the continuous plasma hum, the magnetic field that refused to rotate, the compression of interstellar material at the heliopause, the solar influence persisting far beyond the boundary, the temperatures that redefine what fire means in deep space, all of it forms a single, ongoing measurement of a place no other instrument can currently reach. The interstellar medium is more structured, more active, and more entangled with our Sun than any scientist working in the 1970s or 80s ever imagined. The heliosphere is not a simple bubble. It is a complex, dynamic shield, and the only real-time probe we have inside the space beyond it is a spacecraft that launched on the 5th of September, 1977.
In 1977, the Voyager 1 space probe was launched to study the outer solar system. The 2 Voyager space probes have become the longest operating spacecrafts in spaceflight history.
Carrying 69 kilobytes of memory and wiring partially wrapped in aluminum foil from a Florida grocery store because the proper aerospace shielding was not available in time. It was supposed to die in 1982 after a 4 or 5 year mission to photograph Jupiter and Saturn. It is still alive 49 years later, running on decaying plutonium and the stubbornness of every engineer who has refused to let it go. No funded mission is positioned to replace Voyager 1 within a generation. When the last instrument goes dark in the early 2030s, the continuous stream of measurements from interstellar space will end. The golden record will keep traveling, silent and patient, for tens of thousands of years, carrying a message from a species that once figured out how to build something that could leave home, look back, and still whisper what it saw. We would love to know what you think about Voyager 1's journey and what it might still discover before it goes silent forever. Drop your thoughts in the comments below.